In this module, we are going to start looking at various special cases associated with convective heat transfer, certain applications like boiling heat transfer, and we will also follow this up with a few special topics on experimental analysis, experimental work in convective heat transfer and design of equipment. So, until the last module, we basically presented to you lectures concerning fundamentals associated with convective heat transfer. Most of the fundamentals that we were presenting were typical of undergraduate curriculum with a little bit of postgraduate flavor. We had similarity analysis in detail, we had integral method analysis in detail, there was turbulence taught in some amount of detail. So, typical undergrad curriculum would not have all these topics in great level of details. You will just present the Blasius solution in fluid mechanics and probably talk a little bit about Reynolds analogy in undergraduate curriculum. However, here we have presented all these things in sufficient detail so that there is a feel for how certain things come. So, how beautifully scaling analysis gave us a functional dependency on Reynolds number and how the coefficient was obtained by using simple profiles in integral method, and an exact solution using similarity method also gave us the coefficients in front of the expression for delta or the boundary layer thickness. So, there was a clear logical progression of ideas, thereby where when the correlations come and the students are asked to use those correlations, there is not a feeling that, oh, where does this number come from, how do I know it is Re to the power half, or how do I know it is Pr to the power 1/2 or 1/3, and is this all magic. So, through the lectures that we presented earlier, we have tried to give you a scientific feel for how certain coefficients and certain powers to the non-dimensional quantities are obtained. There is a lot more that can be done, but in view of time and the contents of the course, we would like to shift gear to certain special topics and applications. So, one of the topics that I would think is important is the effect of viscous dissipation. Viscous dissipation is something which was there on the right hand side of the energy equation. When you derived the energy equation, you had rho Cp material derivative of temperature with respect of temperature is equal to the conduction term plus volumetric heat generation plus the viscous dissipation term. And when we did the non-dimensionalization of the energy equation, it was giving us a non-dimensional number, Eckert number. Viscous dissipation was giving us a non-dimensional number which was Eckert number. So, that is U infinity squared by 2 divided by Cp delta T, and this term we said that when Eckert number was very high, as in high speed flows, 1 by Eckert number would be very small, and therefore, we can neglect the viscous dissipation term in most conventional engineering problems, except when you have high speed flows. Okay. So, but viscous dissipation does have some kind of an effect on the flow, and how it alters the heat transfer coefficient is something that is important that we study. There are similarity analysis solutions possible. There are also integral method solutions that are possible. Remember, we had the term when we did the integral method, we took both the pressure gradient parameter as well as the viscous dissipation term. However, we simplified the term for constant of free stream velocity and negligible viscous dissipation, and we got the energy equation that was solved. So, we solved a very special case for flow over a flat plate with Prandtl number approximately equal to 1. However, it would be pertinent to see the effect of viscous dissipation on the Nusselt number and the heat transfer coefficient. So, with this background, let us get started with the governing equation. So, consider the case of flow through a pipe with constant wall heat flux condition. Q double prime is constant, and we are talking of very highly viscous fluid, that is Prandtl number very much greater than 1, and circular pipe diameter is equal to d. And if you just have the energy equation, it is going to look like this: rho Cp dt by dt is equal to del dot k del t plus q dot plus mu phi. And we used to neglect this term. This is the viscous dissipation term. Viscous dissipation is basically the contribution due to the effect of viscosity or the fluid property which causes heating of the fluid. The loss, frictional energy which is lost, that is what is being accounted for by the viscous dissipation term. We are going to make a few assumptions here, and let us list the assumptions one by one. Steady state, volumetric heat generation equal to 0, no volumetric heat generation, flow is axisymmetric, that means d by d theta of anything equal to 0, and also u theta equal to 0. This also we make. So, this is no swirl. This is what we had used in deriving the flow through pipe expression, fully developed flow. That means d by dz of u is equal to 0. You can use the subscript z. It would be pertinent to draw the pipe like this. This is the center line and this is the flow. We are talking of a situation where the boundary layers merge. Remember, Prandtl number is much greater than 1, which means your thermal boundary layer is developing very slowly. This is your thermal boundary layer. This is your hydrodynamic boundary layer here. This is delta as a function of z. I would like to call this as the r direction and this as the z direction. Instead of x is just convention, you can also call it x. So, uz, axial direction velocity, this is z equal to 0, okay, and this is my diameter, dia is equal to d, and this pipe is subjected to constant wall heat flux. Okay. So, du z or simply du by dz equal to 0. So, we also have u of r equal to 0, and this is laminar flow, steady state laminar flow, of course. So, you do not have a component of velocity in the radial direction. Constant properties, Newtonian fluid. So, all those things, mu, rho, everything is constant. Then you also have an important assumption, no, it is not actually an assumption, it is actually a fact. So, from order of magnitude analysis, we can show that d squared t by dz squared is much less than d squared t by dr squared. This can be shown from order of magnitude analysis. Where does this occur? This occurs in the conduction term. All we are trying to say is that for this flow, in this flow, what we are saying is R or D is much smaller than L, first of all. So, we are talking of pipes where the diameter is quite small compared to the length of interest, and the dt by dr is going to be greater than dt by dz. It is quite obvious, because you are having heat transfer like this, you see a profile for the temperature which is something like this, right. So, this is your temperature profile, and at the next z the temperature profile is almost same, meaning numbers change a little bit, no, we are not saying that, but the shape etc. is the same. The gradient in the radial direction, that is this direction, radial direction gradient, suppose the wall temperature is 200 degrees centigrade, you have fluid like water, or wall temperature is 90 degrees centigrade, core is 25 degrees centigrade, you will see a dt by dr where r is capital R would be about 75 degree over a small radius, say your 1 inch diameter means R would be half inch. Correspondingly, if you talk of dt by dz, due to energy balance, the fluid temperature at the same radial location would change by a small amount over a larger distance. So, dt by dz by itself is going to be small compared to dt by dr. This is extremely true if you want to think of in case of a current carrying wire, where you are going to have, you have seen in conduction problems, right. If this is the wire or a solid in cylindrical coordinate, the temperature profile for heat generation case would be like this. This is your T center line is much greater than T wall. This is your T wall or T surface, and T infinity is here, which is the convective part. So, you would say that the profile would kind of repeat itself with a small change in the magnitude, okay, if you are having heat transfer from the outside, as in this case, or if you do not have any heat transfer from the outside, if there is a constant volumetric heat generation, every actual location is going to have a same kind of temperature profile. So, the changes in the radial direction are far more significant as compared to changes in the axial or flow direction, and the rate of change. So, d square t by dt by dr itself is large, r is again small. So, d square t by dr squared is going to be much larger than d square t by dz square. R scales at best as capital R, this is your maximum, but Z scales like L, which is R is much less than L. So, keeping that philosophy in mind, we can say that d square t by dz square, or the second derivative of the temperature in the axial direction, is negligible compared to the second derivative of the temperature with respect to the radial direction. So, with these assumptions, so a lot of simplifications will happen. So, with the above assumptions, this I will leave this as an exercise to you and to the students. The energy equation becomes rho Cp steady state dt by dt. So, dt by dt equal to 0 at steady state. So, the first term dt by dt material derivative, the first term is going to go to 0. Then you have a term of u r with respect to u r dt by dr, u r was 0. So, that would drop off. U theta by r dt by d theta, u theta was 0 as well as d by d theta of any quantity is 0. So, that term also will drop off. So, the only term which is left in the left hand side or the advection term happens to be, and I will just bring the k down from the right hand side, this is rho Cp by k times u of z dt by dz. You can retain this as u of z or simply u. Keeping in mind this is the axial velocity, and remember this is a function of r, pipe flow, right. This is velocity of, if you are talking of velocity profile, this is the velocity profile for pipe flow, laminar flow. This is your velocity distribution. U of r, this is the axial velocity which is a function of radial direction, which is nothing but 2 u m bar 1 minus r by capital R square. So, it is a function of r, right. So, this is the left hand side. The right hand side is going to be only the radial, that is d square t by dr term, this one, only this one would remain, and therefore, I would get 1 by r d by, I have brought k out, constant property. So, I have divided the left hand side and the right hand side by k. So, the k has come out here, 1 by r d by dr of r dt by dr. Volumetric heat generation was neglected, mu by k into viscous dissipation term. Again, viscous dissipation term has many terms. Okay, there it's a d squared u by dr, I mean duz by dr whole squared, and when you expand the viscous dissipation term, which had the first derivative of the velocities with respect to the spatial coordinates. How were the viscous dissipation term created? Viscous dissipation term was created by the work done because of the viscous forces, tau times area into displacement. So, the right hand side of the Navier-Stokes equation had mu into du by dz, second derivative, so on and so forth. So, when we derive the energy equation, we had to take those derivatives into account, and the work done in that, where all the mu terms were there, those were the viscous dissipation term. We grouped all of them. Now, with these assumptions that gradients in the theta direction, gradient of velocity in the z direction because of fully developed being 0, this you will need to do. So, you need to look at the energy equation in cylindrical coordinates. So, I will just write it down for you. I am not going to present the equation here. So, look at energy equation in cylindrical coordinate, energy equation in cylindrical coordinates, and expand the viscous dissipation term using assumptions stated above. So, this can be in fact an exercise that you can give your students, that look at the viscous dissipation term and simplify for this problem. If you do the maths, you would get only this term here. I am going to just mark this in red. You would get duz by dr the whole square, gradient of the axial velocity, axial component of the velocity with respect to r the whole square. Every other term in the viscous dissipation term is going to drop off. So, this can be show from mu phi expression in cylindrical coordinates. This is left as an exercise. So, lot of maths has been skipped in coming to this form. Now, what you need to remember is this equation. Remember when we went through laminar flow, heat transfer, flow through a pipe, we basically had the left hand side like this, the right hand side only had this term, the viscous dissipation term was not there. So, obviously, you got Nusselt number in a straightforward manner. Of course, there was a lot of maths, but you got it as 4.36. Now, this additional term is going to be there on the right hand side, which is going to complicate the maths for us, because this is not a simple term. This has a gradient with respect to r, velocity gradient with respect to r. See, there is a uz which was here on the left hand side, right hand side you have a duz by dr square. So, when I want to integrate the governing equation for the temperature, so we went and got dt by dr and integrated it to give you the temperature distribution. So, when I want to do that integration, I would have to deal with additional term which is having a function of r here. So, things become a little bit complex, nevertheless we will do it. So, this is the governing equation, and this is a second order in radius in radial coordinate, first order in z. So, we will simplify this later on and see what can be done. So, this on simplification, or when I group the terms together, take this is rho Cp by k is equal to 1 over alpha. So, I would get uz by alpha dt by dz is equal to 1 by r d by dr of r dt by dr plus mu by k du z by dr the whole square. This is the simplified governing equation considering viscous dissipation, simplified governing equation considering viscous dissipation. Now, we will go to what we have done in hydrodynamics for a pipe. For a circular pipe, we know u of z as a function of r is equal to 2 times the bulk mean velocity 1 minus capital R by small r whole squared, 1 minus capital R by small r whole squared. And now, if I go to my energy balance, please remember, when I had my energy balance where you just did not have any viscous dissipation, m dot Cp T bulk mean, this is T bulk mean plus dTm, this is my control volume of thickness Z, and this is my volumetric heat flux. I got dTm by dz is equal to q double prime pi d by m dot Cp. Correct? We got this. We have shown this several times. This was the energy balance. Now, what I am going to do is, I am going to keep this in mind, but now I cannot use this kind of energy balance. Remember that the temperature is going to change because of the viscous dissipation. So, this kind of energy balance becomes a little meaningless. Now, if I write du, I got u of z with respect to r, I need du z by dr. So, let me evaluate that. So, du z by dr is going to be 2 times mean velocity into minus 1 by capital R squared 2 r. So, this is minus 4 u m r by capital R square. D u z by dr the whole squared, therefore, which is what I need, is nothing but 16 u m bar squared divided by r to the power 4 times r squared. This quantity is a constant. So, I got the expression for the term on the right hand side. So, it is going to be a number into r squared. Now, I will substitute for this in the energy equation, simplified energy equation which we wrote in the last slide, u z by alpha, u z by alpha. So, this u z by alpha I am going to write in terms of this. So, let us write it. So, 2 u m bar 1 minus r by capital R whole square, alpha remains here, dt by dz as it is. This was my u, divided by alpha. So, I wrote for u, I just substituted the velocity profile, is equal to 1 by r d by dr of r dt by dr plus 16 um bar squared divided by capital R to the power 4 small r into mu by k, of course, sorry, mu by k is also going to be there. Let us manipulate the governing equation. This we can substitute this, but the problem with this is when I use this, when I try to do this, this is not going to be very easy to solve. When we did without viscous dissipation, this worked. Now this is not going to work. So instead of substituting like this, instead of this step, let us consider d by dz of uz of t. This is exactly what we do all the time. This is nothing but uz dt by dz plus t times duz by dz. duz by dz is 0 because of fully developed flow. Therefore, I can write uz dt by dz, which is my left hand side of energy equation, simplified energy equation as shown above, is nothing but d by dz of uz times t. This I will use. So, therefore, my energy equation becomes 1 by alpha. So, it is going to become 1 by alpha d by dz of uz into t is equal to 1 by r d by dr of r dt by dr plus mu by k duz by dr square. So, I have modified only the left hand side, keeping the right hand side same with this simple modification, So, now what is my next step? I integrate this equation with respect to r from 0 to capital R. I am integrating with respect to r from 0 to capital R. So, if I do that, I just write this step. So, 1 by alpha, this is going to be 1 by alpha integral 0 to capital R d by dz of uz into t 2 pi r dr. This of course is 2 pi r dr. You can't, integration with respect to r does not make sense. Integration with respect to area dA, this 2 pi r dr is equal to 0 to capital R 1 by r d by dr of r dt by dr times 2 pi r dr plus 16 um bar squared by r to the power 4 mu by k as it is, 0 to capital R, and you are going to have r squared 2 pi r dr. Okay. So, I had substituted for duz by dr square, duz by dr the whole square, just as here, and now integrated. We will stop here in this module. Next module, we will go ahead with the integration and solution for the differential equation for temperature. The temperature then give us the bulk mean temperature, and then we will get the Nusselt number from there, just as we got the Nusselt number for pipe flow, laminar pipe flow with constant wall heat flux. Thank you.